Excellent. So now we're going to move to our second Melon Scholar, and then we'll have questions for both of them. So delighted to introduce Maria Kyriazi, who is undertaking a PhD, also known as a DPhil in Oxford, who's going to tell us about autophagy and osteoarthritis, which is I'm very interested to hear about. My mum unfortunately succumbed to osteoarthritis, and
really?
Yeah, it was very, very severe and painful. So anything you can do will be very gratefully received. Maria, thanks.
Thank you for the warm introduction. I know it's quite tricky to be after Lauren because it was an exceptional talk, but I'll try to be there. So my name is Maria Kyriazi. I am a third-year PhD student here at the University of Oxford, and today I'll talk to you about osteoarthritis and aging and why it's really important to focus on osteoarthritis research. But before I start, I know that I am surrounded in an audience that has a lot of aging research enthusiasts like myself, but it's something that has not advanced over the last years. It is something that people have been keen since very early on, since the 4th century before Common Era. And we did have people like Hippocrates who described aging as the result of progressive loss of innate heat, the depletion of which leads to death. Then this was followed by Plato and Aristoteles, who further elaborated this theory and considered aging as influenced by the extrinsic stimuli, such as that coming from the environment or the nutrition that influence the aging process. And this was then followed up by Galen, that described the process of getting old as natural and lifelong, and indicating that death derives from the body deteriorating itself. So all these are still applicable today, and many, many more theories have emerged ever since, with people still being very, very interested as to why we age. And though we do have the technologies and we have evolved a lot in the research, we still don't know why we age. What we certainly know is that we are living longer. So this is old news now. We do know that there is a global leap in how much we live, how long we live. And according to the World Health Organization, we do know that by 2015, the number of people that will be older than 60 will go from 1 billion to 2.1 billion. And this is a huge leap. However, what we also look at, what we see is that despite that increase in the lifespan, the number of years we are alive, there is not an equal increase in the health span, the number of years that we live free of disease. And this is really, really important, because this means that you can have people living up to 90s and 100s, but then they can start developing disease as early as since the age of 65. So that gives a lot of years of these people living with severe disease and sort of suffering throughout the remaining part of their life. So older adults are increasingly affected by chronic diseases, and that poses a significant challenge, especially in modern societies. And we do know that the number of these diseases that accompany advanced age are increased with every decade of life. So taken together, these realities, they call for great investment in the aging research and the age-related disease. And they put a flag on making us focus more as to understanding why these processes, what are the processes that change with advanced age, and they make older adults susceptible to disease. So one of the major diseases that we see with advanced age is musculoskeletal disease. And the most common musculoskeletal disease is osteoarthritis. So it is the most common joint disease in the global scale, and it's the major cause of disability worldwide. We do know that every year we have 46.6 million new cases. And we also know that 1 in 3 adults after the age of 65 will develop osteoarthritis. And I know that a lot of you might think, oh, well, you can have OA, but at least it's not life-threatening. You are still alive. Well, it is equally important, and I'll explain exactly at this moment why it is important. The first thing is that you have reduced mobility, you have reduced strength, and you have disability in movement. This is also accompanied by difficulty in performing daily tasks. You have very high pain and stiffness, and if you have anyone in the family that is a patient of OA, like I do, you do know that patients usually avoid to perform daily tasks, like simple tasks as even going out for a simple walk. You also know that you lose dependency and functional decline. And though for years we thought that osteoarthritis is not a systemic disease, there is an evident link suggesting that OA impacts the metabolism. So we have patients that slowly might be more prone to developing diseases like cardiovascular disease or metabolic disease and even obesity. And recent evidence also suggests that there is a direct link between osteoarthritis and neurodegenerative diseases. So recent metadata analysis show that patients with OA are more likely to develop neurodegenerative diseases like Alzheimer's, and there is a direct link, a direct axis between the brain and the joint. And finally, it poses a massive socioeconomic and healthcare impact, which is really important to pay attention in the modern societies. So the current treatments, the gold standard treatment is actually joint replacement. And current therapeutic strategies focus more on pain relief. So it's really, really important to understand what are the underlying mechanisms that make adults prone to developing osteoarthritis and how we can help the older population not develop OA, prevent it or postpone it so that we can help them have a longer and healthier life. When it comes to the biology of osteoarthritis, and I've attached an example of the knee here. In normal conditions, we have the articular cartilage, and this is the soft tissue that supports the joints, and it contains post-mitotic cells called chondrocytes. So under disease, we have severe degradation of the cartilage tissue. We have loss of these chondrocytes. And for years, osteoarthritis was considered as a wear and tear disease. The main sign of damage that people were looking at was the cartilage. Now, we do know that there are other sites that are severely impacted as well. We know that OA joints have mild inflammation that is characterized by expansion of fibroblasts and immune cells that are resident in the tissue. We know that the synovium, which you can see at the bottom picture there, the synovium that contains two layers also alters with disease. So usually the synovium has an outer lining layer that contains fibroblasts and an inner sublining layer. And we know that in osteoarthritis, patients show an expansion in the lining layer, the outer layer, that relates to mild inflammation and more damage and pain. We also know that in severe cases and progressively with osteoarthritis, we develop osteophytes, which are bone-forming regions, as you can see at the tip of the joint, that cause more severe pain and stiffness to the patients. So, having said that, a very, very big significant challenge that we have in osteoarthritis research is the lack of tissue. It's really, really hard to have tissue, and this is because all the tissues that we get in the lab are coming from patients that went through joint replacement. So it's really, really tricky and challenging to understand what happens in healthy aging, what happens in healthy young conditions, and how this alters with aging. So we are focusing more on mice. We have developed two mouse models. The one is to understand the naturally occurring osteoarthritis happening as a result of advanced age, and the other one, the post-traumatic model of the disease. So what I've found so far in my PhD is that with age, naturally, mice develop signs of osteoarthritis. We see that by 24 months, they show severe degradation in the articular cartilage. This is further characterized by formation of mature and sizable osteophytes. And they also show changes in the synovial tissue. And taken together, this suggests that with age, mice can develop naturally occurring osteoarthritis, and therefore we can use them as a model to study healthy aging in the joint. And what I want to understand during my PhD is what are the molecular age-related changes that drive to that shift that creates naturally occurring OA. Another model that we use is a post-traumatic model of disease. So in the osteoarthritis studies, we've developed a model called PMX, and this is partial meniscectomy, whereby we cut part of the meniscus, and progressively the mouse, by 4 weeks of time, they will develop osteoarthritis. And as you can see, this is characterized by severe damage in the cartilage area and formation of mature osteophytes. And so, taken together, we can use these models, the natural occurring osteoarthritis and the PMX, in order to study the drivers, the underlying molecular mechanisms that drive osteoarthritis in healthy aging and in disease. So, what are these mechanisms? What are these age-related mechanisms that we are focusing on? My main focus is autophagy. Autophagy, as many of you might know, is the cellular recycling pathway, which basically breaks down and it recycles molecules and aggregates in the body in order to help them to reuse them and to make them functional again. And though when we are young, this process is very efficient and it works very well, as we get older, it's reduced. It alters with age, it becomes more dysfunctional, and it leads to disease. And this is very important because we don't want to kill cells like chondrocytes in particular, considering they are post-mitotic, they cannot rejuvenate. So it's really important to find alternative ways to keep them back, take them back to their initial state. The other mechanism I'm focusing on is, as Lauren very nicely introduced, is senescence. So senescent cells, as all of you know, they stop dividing, but they are still metabolically active, and they do not enter apoptosis. Or at least they can for a certain extent. So in the lab, I hope you will be able to see it there. So this is an example coming from murine articular chondrocytes. As you see, in normal conditions, they are close together and they are looking healthy and nice. But under senescent conditions, they become enlarged. And as Lynn describes them, they look like fried eggs. Secreting several molecules, SASP factors, and creating more and more damage in the microenvironment and the niche. And we have a lot of techniques in order to study the phenotype of these senescent cells, study the molecular phenotype. One is the established SA-beta-gal. We can look at cell cycle inhibitors like P16 and P21, and DNA damage markers. So taken together, we use these techniques in order to study how these change in healthy aging and in disease. And currently, we're trying to understand a bit further about the relationship between the two mechanisms and how they change with age. As Lauren very nicely introduced, in the lab we took it a bit further. So we use these mechanisms beside the Earth in order to study how they change in the Earth, in the space microenvironment. So people from our group have worked extensively on developing a 3D model to study joint cells and immune cells, and follow up on how these processes change in the space conditions as well. And our group, this is quite old news now. It's been successfully a year since the first launch. The samples are now back in Earth, and our team is working closely on understanding what are the differences between the Earth and the space conditions. And ultimately, what we hope to understand is what is the interplay between the two mechanisms, between autophagy and senescence, and how we can understand a bit better what happens in healthy aging and in disease. And what I hope to be able to answer by the end of my PhD is how do these processes change with age in the joints, and what is the role in osteoarthritis. And taken from that, what we hope to find and take to the next step is to identify novel therapeutic strategies and new drugs that can help to treat or rejuvenate the cells in the joints and help adults with osteoarthritis. So with that, I would like to give a warm thank you to my amazing research team and my even more amazing mentors, Professor Gad Al-Saleh and Professor Lynn Cox. I would like to thank the Melon Longevity Graduate Scholarship. Lauren is the first one. I am the third one. We also have Hamza Ahmad, who unfortunately could not make it with us today, but he's also working on a very important part of aging research as well. And he's not in this picture either, unfortunately, but I promise we do hang out with him too. And of course, the biggest thank you should go to Mr. Jim Melon. We are truly grateful for the support in our work and the aging research. And none of this would be possible today without your support. So I'll put an end here. Thank you very much. And we are both very happy to answer any questions.